Today I'm going to cover a long anticipated topic, ODE45. So first off, what is ODE45? ODE45 is a MATLAB function that allows you to numerically solve initial value ordinary differential equations, or ODEs as I'll be calling the rest of this video. So underneath the hood, MATLAB is using a fourth order run-to-kata scheme, which I highly recommend and encourage you to learn about for yourself or even code if you're feeling very ambitious. Describing this method is beyond the scope of this video, but I will leave a link in the description to the Wikipedia page for it. So you've probably already noticed that I'm starting this video out on PowerPoint slides rather than the MATLAB editor, and that's because there's some precursor knowledge needed to effectively use this very powerful MATLAB function. So let's talk about state variables. So let's consider any given arbitrary system. We can place every state of the system into a vector called a state variable. So here, just some arbitrary state system we have here, which we have this x vector, which has states 1, 2, all the way to state n. And doing some simple calculus, we can use the d by dt operator, and we can calculate the time derivative of our state vector. And this is simply just taking the time derivative of all of the states within that state vector. So let's show a quick example of making a state vector. So let's consider some moving object. It has an x and y position, and it has velocities in the x and y directions. So we can make a state vector, and the different states in it are xy, vx, and vy. And so as we did for the arbitrary state vector, we can just take the time derivative, and we can get the time derivative of the state vector, which in this case is vx, vy, ay, and ax. And so one thing I want you to notice here is that vx and vy appear in the time derivative and in the state vector. So I want you to make note of that because we're going to be using this when we go back into MATLAB land. So the best way to learn about this function is just use some simple example. So let's use some simple differential equation, one that might not be very fun to solve by hand if it's even possible to. I haven't done this, but I don't really want to. So we have d2x by dt squared plus 3x equals 2t squared, and we're going to consider the time interval from 0 to 5. So our initial conditions for this problem at t equals 0, we have x is equal to 0, and dx by t is going to be 3. So what we're going to want to do is we're going to want to rearrange so that the highest order derivative is on the left-hand side of the equation, and we get the equation you see here down below. So let's put this into a state vector. So we have states of x and dx dt. Simple enough, right? So if we want to look at the initial state vector at t equals 0, we can just simply sub in x at 0 and dx dt at 0, and so we can get the initial state vector. Also pretty simple, right? So now let's take the time derivative of our state vector, and we get dx dt and d squared x by dt squared. And then dx dt, we'll notice, is in our original state vector, which is going to be important for later. And we have an equation for d squared x by dt squared, which we calculated on the line above. So if we substitute that in, after we get dx dt still on the top, and then 2t squared minus 3x in the bottom. So now let's return to a more comfortable place, the MATLAB editor. So let's start by saying the magic words, CLC, clear, and close all. I like using close all for making figures. And so to recall what we're doing here, we are solving this differential equation here, which is a second order differential equation on this time interval, and we have some initial conditions that we described just a second ago in the PowerPoint. So the first thing we want to do is we want to define a time vector. So let's say, let's call it t-span, and we'll say that it is linear spacing from 0 to 5, which is our time interval, and we'll have 100 increments. You don't have to specify your time vector like this. You can just specify starting and ending time, and MATLAB will figure out the spacing, but I prefer to give it the spacing. And so let's also give it our initial conditions. So we're going to say x0 is going to be 0, semicolon, 3. So recall from earlier that we have our state vector, which is x and dx dt, and our initial conditions are 0 and 3. And so one thing to be careful of when you're doing this is to make sure that your state variable is in column vector form, because that's what ODE45 likes. So for right now, this is all we need to do to set up our thing for ODE45. So let's go down to the bottom of our script here, and let's make a function. So we're going to see, so what we need to do as coders is we need to make a function that spits out the derivative of this state variable. So let's say function, and so what we want to spit out is dx by dt, and that's going to equal, let's call it f1, and this is given the variables t and x. So we know from the previous slideshow, we know what dx dt is, and it's just another column vector. So the first element of it is dx d little x by dt, which, if we remember, is the second element of our original state vector, which we have here in this function, this big X here. And so we can just say x2. And then recall that we need to give it a column vector out, and then the second element is d squared x by dt squared for the d big X by dt variable, right? And so we solve for that in the PowerPoint, and just to recall quickly, it is 2 times t squared minus 3 times x, but x is going to be the first element of our state variable, so it's x, and then we'll reference the first index here and close that. You can do that. So now let's just hit run, make sure that runs. We are error free. Oh, because I didn't actually call OD45. Let's do that. So the way to do this is we do t out, x out. Those are the two outputs from ODE45, our time vector, and then our spatial solution equals ODE45. And so we can add f1, and then we want to give it our time vector, so we're giving it a t-span, and then we want to give it our initial conditions, which is that x0 vector that we made above. And so now if we hit run, we don't get any errors, and so we have t out, which in our case, since we specified all the time increments, is the exact same thing as our t-span variable. However, if you just gave it a starting and ending time, then this would be more important. And then we have our state variable out. So this is a double column. So this first column here is our x, and then this is dx dt. So let's plot what this looks like real quick. So we can say figure 1, and we can do subplot 2 1 1. So we can plot, let's do t out just so we're consistent here. T out, and then we'll do x out all comma 1. And then we can put x label, and so that's going to be t, and then y label is going to be x. So sub plot 2 1 2, plot t out, and then our first derivative, so dx dt, so that's x out all comma 2. So x label t, and then y label dx dt. So now if we hit run on this, this is the solution to our ordinary differential equation that we had above. And really, for a lot of cases, this is, if you struggle with solving differential equations, this is a lot faster if all you care about is the numeric solution. And in a lot of cases, if you are doing academic research, for instance, you might have differential equations that are nonlinear and can't be solved by hand, in which case you need to rely on numerical methods like ODE45. So let's move on to a more complex example. So in this example, we're going to be solving two simultaneous differential equations. So let's consider the system we have here. We have two tanks. We have tank A and tank B. They both have 10-liter capacities, and they have concentrations X and Y respectively. And so meanwhile, we have a 16-liter per minute inflow into tank A, which has a concentration of 0. We're going to be using molarity, which is moles per liter. Marginally important for the video, but whatever. And so going out of tank A is 25 liters per minute into tank B. And then coming out of tank B back into tank A is 9 liters per minute. And then 16 liters per minute completely leaving the system out of tank B. So this is a pretty just kind of not defined problem initially. So we just know initial concentrations within tank A and tank B. So for tank A, we have X is 0 is equal to 6, or 6 moles. And then in tank B, we have a concentration of 0. So let's find the time rate of change of the concentration of tank A. So we can say that dx dt. So we can do the rates in minus the rates out. And so that's 16 liters per minute times 0 moles per liter. And so that's this inflow here, and that's just going to equal 0. And also coming in is 9 liters per minute of concentration from tank concentration Y, which is going to be Y over 10 moles per liter. And then leaving tank A is going to be 25 liters per minute times X over 10 moles per liter back into tank B. And so we end up getting that dx dt is 9 over 10y minus 5 over 2x. We can do the same process for tank B, and so we can say that dy dt is going to be this 25 liters per minute times X over 10 moles per liter. Leaving tank B is 9 liters per minute times Y by 10 moles per liter. And then also leaving tank B is 16 liters per minute times Y by 10 moles per liter. And so this gives us a final equation of dy dt equals 5 by 2x minus 8 over 5y. So let's go into actually putting this into a state variable. So I've just kind of cleaned this up a bit. So we have our two state equations, equation 1 and equation 2. And this actually does have an analytic solution, which I'm not going to do. But trust me, this is the right answer. So let's have our state vector. So in this, we have the moles of of x and in y. So our state vector is simply x and y. We want to put in our initial conditions, which is that the initial concentration in tank A is 6 and the initial concentration in tank B is 0. Our initial state vector is just 6, 0. We can do the time derivative, and so dx vector by dt is just dx dt and then dy dt. And then if we want to substitute in for dx dt and dy dt, we just use our equations that we have up here. So now let's move back into MATLAB. So now let's get on to coding our second example here, the two tank problem. So we'll start with the magic words. That's CLC, clear, close all. So we're going to do the same process as before. So we're going to say T is equal to lin space, and that's going to be, we care about after 10 minutes, our concentration after 10 minutes. So 10, and we'll do 200 this time for fun. And so we are going to also just hard code what our analytic solution is, because we're going to compare directly with them, and we can see that we do get the same answer eventually. So we're going to say, so we can say that these. So now let's get into our numerical solution. And so we're going to start with our state vector, and we're going to do our initial condition. And so we're going to say our initial condition. So our initial concentration in tank A was 6, and our initial concentration in tank B was 0. Remember, we're using the semicolon here because we have to put them as a column vector for ODE45. So we have our linspace, we have it up here. So now let's go down to functions. So we're going to say function dx dt is equal to f, call it f2, so it's our second example here, and we have t and we have x. And so we have to return again is dx dt. So we can say that dx dt is going to be equal to those two equations that we had before. And so that's going to be 9/10 times, actually I'm gonna do one more thing to make it a little easier just to digest. So we can extract things directly out of this state variable while we're in this function. And so we're going to say x is going to be x1 because, and then y is going to be x2, and this is just going to be a little easier to digest here. And so for our derivative out of our state vector, it's going to be 9/10 times y minus 5/2 times x. Semicolon, go to the next column, and it is 5/2 times x minus 5/2 times y. Then we can close that, close that. So now we can go back up to here, and we can call ODE45. So we have t out, and then x out is equal to ODE45, and that's going to be at f2 t and then x0. So let's run this real quick, and we do not get any errors, which is great. So now we can say figure 3. We can do subplot 2 on 1, plot. You see, we're going to plot our analytic solution first. So we'll say xt. Let's see, we'll make it markers so we can see it easier. So we'll do dash O here, and we'll do marker indices. Let's say marks. And so I should define these marks variable here. So this marks is just so that we can see the solution better. So we'll say marks is equal to 1 by 4 by length t. And so that we're just going to be only making a marker every fourth index within this time vector here. And so we'll hold on, and now we'll plot the numerical solution that we got from ODE45. So we'll say plot, and we'll do t, so this actually needs to be t here, t, and then this is going to be x out, all comma 1. Yes. And so we'll say x label t, y label x. So we'll do the other one now. 2, 1, 2. Plot t, yt, do the same, dash O. Indices, marks. Hold on, plot, and then our numerical solution for the concentration in tank B. So that's going to be x out, all comma 2. And then y, x label is going to be t again, and then y label is going to be y. So now if we run this and plot it, we can see that our numerical solution is line on line with our analytic solution, and this just goes to show how powerful this tool is, especially if you are rusty with your ordinary differential equation skills. You can get just a numerical answer that is very accurate to an analytic solution, and it takes you only a fraction of the time if you're familiar with this code. So thank you all for watching, and stay tuned for any future videos.